So today so far, I think most of the sessions contained about invasive methods. I want to have a focus today in this session with an EEG setup with surface electrodes. And we will use two different stimulation types. So one will be with functional electrical stimulation with a device that we developed, and on the other side we will use a TMS machine, which is coming from another manufacturer, where we control the stimulation through our research environment. So maybe some of you already saw this slide a couple of times. For the BCI concept, we have our subject or patient where we measure our brain activity. As I said today, surface EEG, but it can also be ECG, as we saw this morning already. And the BCI, the brain-computer interface, is analyzing the brain signals, and we get a control signal to control the device. So in our case today, this will be the stimulator, the FES stimulator, and the TMS machine, and then can also see the feedback that the subject gets. In case of the stimulator, we will get the movement on the hand, and with the TMS, you get directly a stimulation of the brain. So for the FES stimulation, we use the eStim FES. This morning you saw the eStim Pro already. From the outside, you cannot really see a big difference because they look exactly the same, only the label is a little bit different. From the inside, it's a little bit different because the currents that we are using for the stimulation are different. And also from the handling point of view, of course. So with the stimulator, we can do muscle stimulation, but we can also do nerve stimulation, for example. And there is a standalone software coming with the device directly that you can use, but we have also an opportunity to control the stimulator, for example, via Simulink, and with that you have a lot of parameters that you can use actually and manipulate. Yeah, as mentioned, fully programmable, but also with the control software, you can do already a lot of applications in principle, but with the Simulink integration, it's more flexible even. Similar as this morning, we also have here a biphasic stimulator, and it's medically certified. So we use the system mainly in our RecoverX application that you will see later this week, but you can also use it for research purpose, of course. So in Simulink, when you use it there, it's out of the certification range, of course, because the software is not certified, but the device itself has the certification. The main settings that you do when you do a stimulation are that you set the stimulation phase amplitude. So that can be, it starts from 1 milliampere going up to 60 milliampere. Usually when you do the stimulation, we will see it afterwards with my colleague, yeah, around 10 to 15 milliampere is enough to get a proper muscle movement, for example. But it depends, of course, on the muscle that you want to stimulate. So for the lower limb, for the arm, for example, around 10 to 15 milliampere are fine. For stimulation of a leg movement, for example, you need higher currents because the muscle is bigger. But also when you work with patients, for example, the currents might be higher that you need for the stimulation because yeah, patients have maybe spasticity or because of like movement disorder, it's simply hard for the stimulator to get the proper movement directly done with a lower current. The phase duration can also be adjusted from 50 to 400. And yeah, as mentioned, the shape is typically rectangular. So when we do the stimulation, as mentioned, it's biphasic. So we have the pulse here. What you can also actually set is an interface duration phase. So that's optional. So it's not necessary to use that, but you can. So then you will see that the shape is a little bit changing here, like that. And this is how it's typically described in the software also, when you set the parameters. So you can modify the phase duration. You can also set the interface duration, interval, for example. And altogether, what we see here is then called on one side the pulse, and also the pulse onset interval. When we combine pulses, we create the so-called train. So that's how we defined it in the software, and how it's called there as well, when you set the parameters. I want to switch now to the practical part in principle already. I have some more slides, but I will show them a little bit later during the experiment, because today what I want to show you is a motor imagery experiment where we will control the stimulator by imagination of a movement, left and right side, and therefore I will prepare now my colleague, and then we will do a training session with him. This takes anyway a couple of minutes, and while we do that, I will explain a little bit more in detail about the features of the system. So I will just stop the sharing shortly, and I will share the screen now. So now we are in the MATLAB environment, and we are using the g.tec software from our side. You maybe heard it yesterday already. It's a big package for online processing, a lot of functionality included, where you can directly use our equipment in MATLAB Simulink. So when you use, for example, the Simulink library, you see there are a lot of applications actually already available here, with different BCI applications that are ready to use. So you don't have to develop anything yourself. You can directly start with that, and you have directly the option to run the experiments. But of course, you have the flexibility to modify those, or to make your own blocks and functions. What I want to use today is this model that is called the motor imagery common spatial patterns with FES. So this is directly integrated in the software that we will use today. So I have prepared that already before. Only to speed up the process a bit. So what we can see here is we get from the block our signals. We will configure it then, and here we visualize the data, and here we are doing the processing of our data. So after some filtering, we calculate the CSP, and calculating a variance, normalize the data, and then we apply a classifier if we have one, of course. So for the training, there is no classifier available yet, but afterwards we can calculate it based on our training session. What we can do also here, in the BCI paradigm, we can define if we want to have feedback or no feedback. So at the moment we have no feedback because it's the training run. When we have feedback, we need the classifier to calculate actually the and get the feedback then with that. Below here, sorry, the dog is also in the room and missing Christoph. Here we have the parameters for the FES control. So we have practice run and rehabilitation run. So in the practice, we get always the stimulation from the device, from the two stimulators. And in the rehabilitation, we have really the control through the EEG. So what I will do now, I will also just switch shortly the camera that you can see that probably better. And I will just deactivate the background image. So you can see my colleague. I will maybe shortly stop the screen sharing again so that you can see our video easier. So what I will do now is first I will mount the FES electrodes. So he's simply putting his hands on the table. And I am cleaning a little bit the skin also on both sides. And we have here our electrode pads. These are the ones that we use for the upper limb stimulation. So Evgeny, please make a movement of your wrist so that I can feel the muscle. So these electrodes are directly, with kind of a glue so that they are stable on the hand. Then we do that also for the other side. So again, movement. So the electrodes are placed. I will maybe shortly share again the screen. So here we have two blocks now for the two stimulators. So we want to stimulate both sides. Therefore, the two devices. So we start with the right-hand side. So here you have the window that you can use for the configuration. So here we have our main settings. We had like the phase duration. Typically for upper limb movements, we use around 300 milliseconds. And here we have the amplitude that we can adjust. Now it's low. We will increase it step by step. You get also some information about the battery and so on. There are also advanced settings available here that you can see. So where you can, for example, define the interface duration interval that I mentioned before, and also how long your train, the whole train in principle, should be. So in this case, the motor imagery part takes around 3 to 4 seconds. So that's why I defined this this range here. So the train, the whole one, is around not exactly 4 seconds, but approximately. So when we do the settings here, as a first step, we have to activate the stimulator. And then we can start with the stimulation. So as I said at the beginning, it's very low, but then we can increase it. It stops always, of course, now after around these 4 seconds. So we stimulate again. So you can see we want to get a wrist dorsiflexion. So we are almost there, pretty good. So in this case, we need probably around 14 milliampere to get a good result. So that's for the first stimulator. Then we move to the second one. You always Here also a little bit of a buzzer sound when the stimulation is done. You probably cannot hear it at the moment that well, but that can be also done from the stimulator side. So that's now for the left-hand side. So we activate again and we stimulate. So we increase again. Yeah, here it's even with a little bit less current. Maybe the positioning of the electrodes is a little bit better. Directly hit the spot. So with this setting, we are fine. And now we can move on and mount the cap. So maybe I will switch again and stop the share so that you can see that. In this case, I'm using a cap with more electrodes, but for the experiment, we will use only actually 16. And those are the super flat electrodes that we are usually using for TMS recordings. So where you can really go very close with the coil. I think Christoph mentioned them already yesterday. So we put on the cap. We check for the positioning. So, and then we take our syringe and like my colleagues also showed it yesterday, one by one, we put gel there. For those ones, you have to take care a bit because they are actually they're actually a little bit as they are so flat, there is not really so much space there. And you don't need a lot of gel. The others, like the Scarabeo electrodes that we also have, for example, they have a little bit of a gel reservoir because there is the holder ring that we are using. And in this case, then you have simply a little bit more, a bigger area, but as they are so flat, there is almost nothing here. But the principle is the same. So with the tip, you try to reach the skin again and fill it up a bit so that you see the gel is coming out slightly on the top. So we use 16 electrodes over the motor area. And then there are some more in the back. And another one. So I will share the screen again. Now we check for our amplifier. Have a look. Yeah, that is okay. Sorry, the device cannot be found. Just a second. Can always happen in these live sessions that something is not working properly. Let me close maybe shortly the model and start it again. It's not there. Oh, I got it. Let's try it again. Seems that MATLAB crashed also. So let's give it another try. Yeah, these conditions are not always optimal for real-time experiments, of course, because usually you're not running Zoom. So now we have our high amp available. And we configure it. So we select a sampling rate of 256 Hertz. As I said before, this cap has 64 channels. So I'm using only 16 of those. So that's why I have this selection here. These electrodes are mainly located over the motor area. So that's why I've selected these. And I also do some pre-filtering of the signal already. We probably have to set shortly the stimulation again. And then we directly can start. Sorry for that, but yeah, online demos, always something can happen. So we try that again. Right-hand side, the value from before was stored. So let's try if it works still. That's fine. And also for the left. So we activate, we stimulate. That's fine. So Evgeny's task is now to concentrate on the stimulation and on the motor imagery. So he will get the task. Okay, you imagine a movement of the left or right hand side, and according to that, he should try to imagine the movement. This will take a couple of minutes now, and I will explain you in the meanwhile some more details. But first we will have a look on the signal, if that's fine as well. So we check in our scope. And we set our parameters for EEG. So here we have our 16 channels. So maybe we can ask Evgeny to make some eye blinks. And also like clenching. So we see artifacts. That's good. The signal is fine. And I will stop the model shortly and start it again. So Evgeny can see this screen now. I also activate the stimulators. He see the fixation cross, and now it's asking, okay, imagination of a left hand movement, and while he's doing the imagination, he gets the stimulation on the corresponding side. I will shortly stop that share again. And I also switch the camera. And yeah, I want to explain you a little bit in detail about the stimulator. So you see here the stimulator from the front side. We have, or can you see it already? Let me just double check. No, I have to share, sorry. So here we have our stimulator. Front side, we have the plus and minus for anode and cathode, where we connect our electrodes for the stimulation. And we have here, an LED that is indicating, okay, now we are stimulating, now we are active. There is also an indication of when the battery is getting low, for example. There is also here an indication with high impedance. So for example, if the electrodes are not well connected, maybe they are loose or already old, for example, you can use them several times, but after some time you have to renew them. Then you might have problems with high impedance. So then, the stimulator will stop directly, and you have no opportunity to continue. You have to check the setting and restart everything. And also there is an indication if the currents are too high or higher. So here it's with 10 milliampere, then the LED is on. It's still not too high, so no problem on that. Anyway, the stimulator has the currents are still low, so it's not no issue that you will hurt anyone. Here there is also the opportunity to connect the hand or foot switch on the front, but we control the device now through the software simply. On the back side, the stimulator is using 2 9-volt batteries that you have to put in there. You can also use some rechargeable batteries since an update for a while ago. And yeah, on the other side, on-off switch. Here you have a connection with the USB, so to connect the device to your computer. And you have also options with digital inputs and outputs, so that you can use it, for example, to get triggers or send triggers from the device. So for example, if we want to synchronize with a hardware triggering, you can also do that. If you want to also have a hardware trigger when exactly the stimulation happens, we also know that from the software already also, but you can also combine that with your amplifier. So here you can see a little bit more in detail the electrode placement for the wrist dorsiflexion, for example, where we use these smaller electrodes so that we had mounted on Yevgeny's arms. There are also other options with these bigger ones. So when you do the an ankle dorsiflexion on the leg, for example, then you use those bigger pads because with the smaller ones, the current would probably be too high when it's distributed over the smaller area. Then you need a lot of current if you want to stimulate the bigger muscle, like for the leg movement. And therefore we have the bigger pads because then you have a bigger area that you use for the stimulation, and then you are not facing issues with high impedance. Yeah. When we do the recordings, main problematic points could be like that people have a lot of hair, then you might need to remove the hair if you do regular treatments, for example, with patients. But typically that's also not really a big problem. We had cases when you use it very for a longer time that you have, and also with high currents, that you might have, yeah, a little bit of issue on the skin, so that it's getting red, or maybe even like a little bit, not really burnt, but that it's simply a little bit irritated. Yeah, these blocks are in the software included. And as we had it before, so all of the parameters are adjustable. In the rehabilitation software that we provide in RecoverX, for example, there you have only like a standard setting, so you cannot modify anything except the phase duration and the amplitude, of course. All the other features are directly configured from our side, but in the Simulink software, for example, you are completely flexible and can do whatever you want here with that. So let's have a look. I think we are almost done. Yeah, exactly. Let me switch the camera. And also let me stop with the screen share and share the other screen again. So Yevgeny did now the trials, 40 trials, left and right hand side, randomized. And what we do now is we have to analyze the recorded data set. So with our offline analysis software called GBS Analyze, you can analyze the data to calculate the classifier. So what we do is we load our data set, first of all. It's this test file that I recorded here. Might not see that much at the moment, but we can adapt the scaling. So we recorded actually, I said like 16 channels, but as you can see in the overview, we have 18 channels. So the first channel is added automatically by Simulink, which is the time channel, and then we have our 16 channels, and the last channel is actually our trigger channel, which includes the information when the stimulator onset happened. So what I will do shortly here, that you see the signals, is that we apply here a different scaling for those. because then we also see some signals actually. Now you can do, of course, a lot of processing steps in the software. What we also provide with the software is like a so-called batch mode or script mode, where you can define scripts and run them automatically directly with all the functions that you want to include in your processing. So it's not necessary to do all the steps always one by one. With the scripts, you can easily do that. And what we are now calculating is a classifier with our 2-class experiment that we had here. So check. Where's my mouse? You can also remove artifacts and automatically with this batch. Now it's creating the classifier, and also we get some plots. Takes a few seconds that this is done. And I can show you that the results that we get. So some CSP plots on one side. Also here classification output of the classes. So you see the blue line is the classification for right-hand side, and the green line is for the left-hand side. And we also get an output of the the 2 classes. So on one side it's again class 1, class 2, and here we have the total error rate. So as you can see, we reach almost around 10% error rate, so 90% accuracy, pretty good. For the other class, like the first class, right-hand side, it would be almost 0. So very good result here on this side. The other side is a little bit higher, but also very good. So he will be able to control it. So here you can again see the whole outcome for this experiment. We closed it now, and I only want to check shortly if he's now able to control the software. So we go back to our model. What we do now is in the apply classifier block, we add the new classifier. Where we have it. So this one, this classifier CSP2 classes was calculated. We open it, and then we can see here the different classification times together with the different error rates. So at after around 6.5 seconds of the trial. So the trial always consists of like, okay, concentration, fixation, cross, then you see the arrow left or right, and then you do the imagination of the movement. So here we get the lowest error rate, and we accept that for our classifier. So in the model, we also change now to feedback, so that we get the control directly depending on the motor imagery, and we also switch to the rehabilitation. So only when it's correctly detected, we get the stimulation actually. I don't want to run a complete run again now, only shortly to see if he's able to control it or not. So task is the same, but now the feedback will only be provided when the PCI is actually correctly detecting. So you see in the middle, the bar is moving to the left or right, depending on the classification result. And with that, if it's correct, we get the stimulation on the left-hand side, for example, in this case. If it's not correct, there is no stimulation. So left he can control actually quite good. Typically during such an experiment, nobody would talk and it would be silent. So a little bit hard, of course, then for him to concentrate. But I think you got the idea, and we saw that it's working actually. Okay. So that was one of the demos that I wanted to show you. So in this case, the device was controlled through the software directly. So we have a programming interface for the stimulator, so you can control it there. But sometimes you have devices that are standalone devices, so you have no programming interface directly. What we can then use is that we trigger the device from our side, from the software. So for that purpose, for example, some of you maybe joined last year. And in this case, we had an experiment. Let me just check. We had an experiment that looks like that. It's a recording of for the TMS setting. And actually what we are doing here is we calculate evoked potentials depending on the stimulation that we get. In the lower part, what you can see is that we trigger the stimulation actually from the software using, in this case, a band power calculation where we can calculate, for example, alpha activity. So that's a common setup where you use alpha activity, and then depending on that, when you detect alpha, you stimulate. In this case, you see this block here that we used last year, for example, was based on the Stimbox. This is actually this stimulation box that we provide, where you have on the outside ginge connectors, and you can directly from there then use a trigger cable and connect with the TMS system. TMS systems are typically using BNC connectors. So let me just show that to you maybe. So this is the TMS system that we use. Sorry. So this is the TMS system that we use, and it's from Mac and more, but there are of course many other systems available on the market. And on the back you have digital or triggers here, sorry, where you can connect a trigger cable. On one side, a trigger cable to start the stimulation of the device, and on the other side, a trigger output where you get the output from the system when the stimulation actually happens. What we are doing now is we connect on both sides a cable. On one side, because we want to trigger the stimulation. On the other side, we want to know when we get the trigger from the stimulation so that we can face the delay. With the Stimbox, we had here around 20 milliseconds delay. But for those of you who followed this morning, we tried also other systems for the triggering actually, and we used so Capella Christoph showed it this morning with a Arduino controller to generate the trigger pulse actually, which is at the moment the fastest option that we detected. And also for this TMS setting, we can use that. And maybe I will shortly show that to you in another model. So for that purpose, we would need to place the stimulation coil, of course. I must say I'm not really an expert for this, the placement of coils, but there will be another session this week by my colleague. Yeah, you can. So Slobodan will show you on Thursday recordings for TMS. And in this session, I want to mainly show you how you can trigger the stimulation. So, and for this purpose, we have only a small testing example that I want to show to you. Maybe I close the other windows because that's always a little bit critical in MATLAB if we have so many things open. So here we generate through this through this pulse stimulator. Sorry. Through this pulse stimulator here, we generate our pulse for the triggering to stimulate. And I have shortly a look if the TMS system is. Do you hear me now again? Sorry. Yeah, with the movement, it was probably. So yeah, we want to stimulate now here the system. And let's have a look. I start the model. So here we have the three triggers in total. So the first one is coming from our pulse generator. So it's always the same, as you can see. The second one is the trigger we actually send to the system. And the third one is the trigger that we get from the system. And is that, we can also include this information. Just a second. Okay, it's not displaying, unfortunately. Okay. Anyway, so the delay that we get here is approximately, in this case now, 9 to 10 milliseconds. So we are around 2 times faster with the stimulation. And what we can do now, so this was only, the triggering was only coming from the pulse generator. What we can do now is to try that if we can stimulate again, come with the stimulation from the alpha activity actually. So therefore we can use this model. This model doesn't include all of the evoked potential calculations, only the triggering part. In case of the TMS recordings, Slobodan will also go further into detail in that. We use typically higher sampling rates of around 4,800 Hertz. And important is that we, of course, enable always our trigger in the configuration. We use now the same setup as before, and we use the channel more in the back for the calculation. So let's have a look. What we can do here, we calculate the band power. And we have here our threshold scope. So just a second. This is our threshold scope, and sorry, the acquisition maybe stopped. So when he's getting relaxed, then the activity will go up. But first, let me set a threshold. So let's try around 100. So can you relax? Maybe close the eyes. So you see when he's closing the eyes and we reach the threshold that we define, we can actually trigger the stimulation. I don't know why the model stops always. And of course, this principle you can use then also for other settings, like, okay, we can activate with maybe when doing imagination of a movement again. So things like that. Simply to get an idea, again, this block here is controlling the Arduino. So with that, when our threshold scope here detects, okay, now we reached the level, then we send out the trigger to the Arduino for the stimulation. And then we close again the loop. So you stimulate directly from the brain activity, the brain region of the TMS system. Can also be other devices then, of course. So that was what I wanted to show you mainly today. On one side, you can use programmable devices directly through Simulink, or you can also use, of course, external devices. Here, timing is very often the main issue, but with defined setups, you can reach quite good timings here, like we saw with 9 to 10 milliseconds. We have to investigate here further. So this is still prototyping, where we can maybe get better results and do more studies and recordings mainly on that. Yeah, we reached almost 1 p.m. now, so I stopped the share and I switch also the camera.
Thank you, Alex. Thank you for all the demos. We already got some questions. So Shankar is asking, based on the trials that you have seen, what is kind of the maximum duration for the neurostimulation with the FES, and according to the comfort for the user?
Hard to say what really the maximum would be. So in the rehabilitation sessions that we are usually doing with the stimulation, we use it takes around 45 minutes approximately, where they do 240 repetitions of this stimulation left and right side. Probably it would be no issue if you do more, but of course concentration is the biggest problem, because to keep on this level of concentration that you are able to control the system for so long time, people are getting tired after a while simply, and the concentration will decrease, and then you will probably have not a really good control for doing the task. I think that's the main issue. And yeah, with this 45 minutes approximately, we are still in the range where it's okay, but I don't recommend much longer, but you could do, of course, longer.
Thank you. So when we talk about the GE Stim FES, is it the same as in the RecoverX, or would it be only for research?
It's actually the same device. So the eStim FES is part of the RecoverX system, but yeah, we have the opportunity to use it also in a research environment with the HiSys software. So yeah, if somebody has a RecoverX setup in principle, then that's a benefit, because then you would also have the opportunity to do research. Then the people are simply more flexible if they want to maybe run their own paradigms and define the paradigms themselves simply, because that's not possible with RecoverX. But yeah, for research, this is an option.
Thank you. Then another question is, can you share more details about the classifier from the multi-imagery experiment? So what were the features, and how did you make a decision?
So as far as I know, the main calculations are based on common spatial patterns, and in the classifier opportunity, then we use an LDA classification for weighting the features. Other methods would also be possible, like a support vector machine also in principle, but for most of our PCI applications, we use like LDA. I hope that answers the question.
That's good, thank you. All right, then one more question. So how is it possible to use the HiSys without the knowledge of the mathematics behind for the signal processing? So how can you start up an experiment?
Yeah, so if you're not really familiar with the Simulink library from our side, it's growing since around, I think, 20 years almost. So there are a lot of functions there, and they are coming from g.tec and validated, so you can use those directly and put your signal processing there. So you saw these models that we prepared for example. You can also easily do that. Simply drag and drop the functions as you need them, or if you need help, of course, we are also happy to help if to set up a model if together if needed. Yeah, and then if you are more experienced, as mentioned, you can include your own functionality and program MATLAB, for example, your own block function and include it there. That's very flexible.
Okay, thank you.